Good afternoon, esteemed speakers, distinguished guests, and my fellow presenters. It is my privilege to be here today to share about my topic, wine quality assessment using machine learning. So first, starting with the project overview. Wine quality is a complex, multifaceted topic that can be approached from the viewpoints of the wine industry as well as the consumers. From the maker's point of view, knowing the wine's quality and ensuring a steady output are essential industry objectives. Exploring several machine learning techniques that include random forest classifier, cardboast, and ensemble machine learning algorithms for the purpose of predicting wine quality helps to reduce human intervention in the quality assurance process by automating it using the product's current features. So, how do we proceed? Firstly, we begin with data collection, followed by data preparation, choosing a model, followed by training the model, evaluating the model, and finally making the predictions. So, coming to the first step, that is data collection, the 21st century model wine dataset is obtained from the website of IEEE Dataport. The two datasets which are related to the red and white variants of the Portuguese Vinea Word wine are obtained from the UC Irvine Machine Learning Repository. So next, coming to accessing and exploring the datasets, the Python pandas read CSV function is used to read or load data from the CSV files. The df.head, df.shape, and df.info functions are used for exploring the datasets. For the purpose of data visualization, we have incorporated the use of correlation matrix, which is plotted for all the datasets. So coming to the next part, that is data preprocessing. Data preprocessing is carried out to clean the data so as to use it in an efficient manner. Data must be cleaned before it is fed to a model in order to obtain accurate results. So coming to the first, that is handling missing or null values. In the Bordeaux wine data set, we can see that the price attribute consists of some NA values. But for these NA values to not interfere with the accuracy of the result, we have dropped the corresponding rows. So coming to the next data preprocessing, that is feature selection. It is the process of reducing input variables in the model so that only relevant data is used and we can get rid of the noise in the data, so we can explore the correlation matrix of the datasets to find out and select the right set of features. So the first question is, what is a correlation matrix? A correlation matrix is a statistical technique used to evaluate the relationship between each pair of variables in a data set. In order to quantify this relationship, the Pearson correlation coefficient is used, which is the measure of linear association between the two variables whose value ranges between -1 and 1. So, the main question is, how does correlation matrix help in feature selection? So, features with high correlation are linearly dependent and hence have almost the same effect on the dependent variable. So, when two features having high correlation, one of the two features can be dropped. So, the next is detecting and treating outliers. An outlier is a data item or object that deviates significantly from the rest of the objects. The box plot representation can be used for checking outliers in the data frame of all datasets. So we can implement the interquartile range method to remove the detected outliers. The interquartile range method is equal to Q3 minus Q1, where Q3 is the upper one and Q1 is the lower bound. The lower bound is Q1 minus 1.5 into IQR. The upper bound is Q3 plus 1.5 into IQR. Any data point less than the lower bound or more than the upper bound is considered as an outlier. So why only 1.5 times the IQR and not any other number? So the number 1.5 clearly controls the sensitivity of the range and hence the decision rule. A bigger scale can make the outliers to be considered as data points, while a smaller one may cause the data points to be perceived as outliers. So we are quite sure that none of the cases is desirable. The next data preprocessing step is handling imbalanced data set. What is an imbalanced data set? An imbalanced data set is when the number of rows or frequency of data points of one class is much more than the other class. Hence, the ratio of the value counts of the classes is much higher. For handling the imbalanced dataset, we have made use of the SMOT, that is the synthetic minority oversampling technique. Oversampling means simply to oversample the minority class using replacement. The SMOT generates virtual training records by performing linear interpolation operations between the existing minority samples and their nearest neighbors within the same class. The advantage of SMOT is that there is no generation of duplicates and synthetic data points are created which are slightly different from the original data. So coming to the next step, that is data sampling. The data is split into training and testing sets using the train test split function. It is basically 80-20 split where 80% of the data set is used for training the model and 20% of it is used for testing purposes. So now we have the different classification algorithms that are incorporated to perform the predictions. Firstly, we have the random forest algorithm, which is used for both classification as well as regression problems and helps to improve the accuracy by solving the problem of overfitting. Next, we have the light GBM classifier, which is based on gradient based one side sampling and exclusive feature bundling algorithm and helps in faster training speed and better accuracy, encouraging leaf-wise tree growth. Next, we have the cat boost classifier, which yields good results without extensive data training and handles categorical features and missing values automatically, which is built in cross validation. So coming to the next ensemble classifier techniques which are incorporated to perform the predictions. Firstly, we have the stacking ensemble classifier which comprises of the level 0 base models and the level 1 meta models which are combined to make predictions from numerous machine learning models on the same dataset. Next, we have the max voting ensemble classifier, which is one of the simplest methods of integrating predictions from different machine learning algorithms. And finally, we have the bagging meta estimator classifier, which is used to entail averaging the predictions from many decision trees that have been fitted to various samples of the same dataset. So coming to the results and discussions, the bar plot representation of the accuracy scores for the different predictions are as shown in the slide. We have also plotted the confusion matrix in different cases which will help us to obtain the false positive and false negative so as to carry out our predictions in an accurate and fair manner. So finally, coming to the conclusion, the main objective of this project is to create a system that would predict wine quality and do so with high accuracy, improve the quality as well as the sales of the wine. And then we have the future prospect of the project, which includes that we can incorporate different kinds of wine, develop a user-friendly GUI which will demonstrate the wine quality percentage, and also other varieties of evolutionary algorithms may be used with the suggested framework to produce a classifier that is more dependable. Thank you everyone and wish you a good day ahead.